Hello, I am Professor Naumov from Central Connecticut State University, and I am going to present you the results of our study of the combustion of bio-derived fuels enriched with aluminum powder in lab-scale hybrid propellant rocket motor. My co-authors are faculty member Dr. Al-Masoud and students which are listed here. Two students are currently in this room. They are Hunter Collins and Aidan Bowser. This is plan of my presentation. I am going to speak about advantages of a disadvantage of conventional fuels and paraffin-based fuels, let's say bio-derived fuels, and describe our results of the study of regression rates of advanced fuels, which are mostly paraffin, beeswax, and paraffin and beeswax enriched with aluminum powder, and let you know about the results of our study of combustion of these fuels, and describe some challenges which the research team faced with, and discuss the results of the study of combustion, its current study, combustion of pure paraffin enriched by aluminum powder. Briefly about rocket engines, we can split all rocket engines in three different groups: liquid propellant rocket engines, solid propellant rocket engines, and hybrid propellant rocket motors. Each of them, of course, has both advantages and disadvantages. And speaking about hybrid propellant rocket engines, rocket motors, these rocket motors combine disadvantage and advantage of liquid and solid propellant engine, because if you look at this diagram, it's clear that hybrid propellant rocket engines use as a rule liquid or gaseous oxidizer, which should be stored in the tank, and solid fuel, which is stored in the combustion chamber. Advantage of hybrid propellant rocket motors compared to liquid propellant rocket engines and solid propellant rocket engines: relatively simple design, especially compared to liquid propellant rocket engines. That's why they are less expensive, relatively low toxic compared to liquid and solid propellant rocket engines, and they are saved for the operation and storage, and we can change the thrust, the value of the thrust and direction of the thrust, and even terminate, cut the thrust of the engine, which is impossible, for example, for solid propellant rocket engine. One of the important parameters of all rocket engines, of course, is thrust of the engine. Formula represented here. In application to solid hybrid propellant rocket engine, it's very important, by the way, for all engines, to know mass flow rate of fuel, which is here, and mass flow rate of oxidizer. But specific features of such kind of engines, hybrid propellant rocket engines or motors, is combustion of solid fuel grain, because it's combustion on the surface in the volume of the in the free volume of the combustion chamber, and in a flow and in a case of injection of oxidizer from the oxidizer tank. That's why mass flow rate of, it's not easy to find mass flow rate of fuel. Mass flow rate of fuel could be represented by density of the fuel, solid fuel, times regression rate, times variable surface of the grain port. The important parameter, which is not easy to obtain, is so-named regression rate, R dot. Because regression rate is complex function which depends on mass flow rate of oxidizer, because it's flow of oxidizers through the grain port, mass flow rate of fuel, pressure in the combustion chamber, even geometry of the grain port as well. Speaking about fuels, conventional fuels of hybrid propellant rocket engines are listed here. It's we can find a lot of conventional fuels. For example, polybutadiene, polybutadiene, hydroxide terminated polybutadiene, and others. And oxidizers could be oxygen, liquid or gaseous oxygen, nitrous oxide, nitrogen tetroxide, and even more. The problem of these conventional fuels is, let's say, disadvantage. These fuels as a rule have high melting point. For instance, you can find here a melting point, melting temperature of HTBP, which listed here. It's about 240 degrees Celsius. So it takes a lot of amount of energy. Consumption energy is very high to evaporate this fuel, to evaporate this fuel and get the combustion. That's why the combustion efficiency of such kind of conventional fuels is not very high, and these fuels of course have low regression rates. It would be much better to find fuels with low melting temperature, low evaporation temperature, and low value and high values of regression rates. There are a lot of options, some options, let's say, to have alternative fuels. For instance, cryogenic solid fuels. Yes, we can use cryogenic solid fuels, but they fuels, because of cryogenic temperatures, have a lot of problems. Multiple pores increase the burnout area of the fuel grain. Yes, it's possible. Then maybe employment of some additives such aluminum powder, magnesium powder, and others, because we know that aluminum powder and magnesium powder have very high combustion efficiency, combustion temperatures, and can increase finally regression rates of the fuel. Or it's exactly what we start to study about 10-12 years ago. Employment of bio-derived fuels such as paraffin, chemical formula is here, beeswax, chemical formula is here, even lard and others, which have as a rule low melting point. For instance, look, beeswax melting point is just 62 degrees Celsius compared with previous slide. Of course, it's much less. That's why these fuels, bio-derived fuels, can provide us with low melting, with high regression rate. They are also non-toxic, not explosive, and can, because of low temperature of melting, evaporation, can create high engine thrust and other parameters. Well, also, it's possible to consider these fuels with additives, with, for example, aluminum powder and magnesium powder and other additives. We can find a lot of information about incorporation of the additives and sometimes very opposite data. For instance, it's possible to find that if diameter of particle size of aluminum powder is about 0.05 up to 0.1 micrometers, it's possible to increase the regression rate. But if we increase the diameters, use aluminum powder with higher values of the diameters, look from 40 to 400 micrometers, unfortunately, the researchers didn't see any increase of the thrust, of the regression rate and the thrust. So in our study, we used 150 fully refined paraffin wax, and corresponding, when we study combustion of the paraffin wax with aluminum powder, we used this aluminum powder with particle size for a size from 22 to 30 micrometers, so it's something like between this range and this range. Well, so long-term project goals, because the project was started about 12 years ago, and long-term goal was find experimentally regression rates of bio-derived fuels, combustion of bio-derived fuels, and these fuels with aluminum powder. We performed the study of the combustion of pure paraffin, pure beeswax, beeswax with aluminum powder, and current study was oriented on the study of combustion of paraffin, of paraffin with aluminum powder, and comparison of the combustion of pure paraffin with paraffin enriched by aluminum powder. Our results were represented by different functions, different regression rates. Regression rates is a function from mass flow rate of oxidizer, mass flux of oxidizer, mass flow rate of propellant, so it's total mass flow rate of oxidizer plus mass flow rate of fuel, regression rate versus in-chamber pressure, and several years ago we proposed brand new regression rate formula. It's regression rate versus equivalence ratio. On the next slide I explain what does it mean. And of course, another goal was represent research component into the undergraduate program, undergraduate curriculum. About equivalence ratio, I already mentioned about equivalence ratio. So equivalence ratio, Equivalence ratio is the ratio of oxidizer to fuel ratio, mass ratio, to stoichiometric oxidizer to fuel ratio. Stoichiometric means that it's complete combustion of fuel and oxidizer, and stoichiometric ratio provides us with maximum combustion temperature. It's sample of the plot of the temperature of change of combustion temperature versus equivalence ratio, and this maximum value of the temperature corresponds to equivalence ratio, which equals to 1. Because it corresponds to stoichiometric oxidized to fuel ratio. But in real life, it would be better to cover all possible ranges of equivalence ratios. That's why our goal was, general goal, cover equivalence ratio from 0.3, which is this part of the curve, change of the temperature, which means that here we have combustion of fuel-rich mixture. And up to 6, it's right side of the plot, where we can observe the combustion of oxidizer rich or fuel lean mixture of combustion products. In order to cover this regression rates, it's a huge range, by the way, we performed the tests of the combustion of 4 different cylindrical grains with the initial and inner port diameter starting from 0.5 inch and ending with 2 inch. In this case, we can increase the mass flow rate of fuel, so move to the left part of this plot. Also, in order to be somewhere here, we try to provide different oxygen supply pressures. So our oxidizer was oxygen from 40 to 200 psi. So such combination of 4 initial diameters of the grain ports of the grain, solid grains, and set of the supply pressure of oxygen allowed us to cover this range of equivalence ratios. Well, on this slide you can see fluid control system, diagram of fluid control system, and it's very complex diagram and very complex design of the test facility, because first of all it's engine itself. The picture of the engine is here, and I just posted here important component of the engine. And as you see, solid fuel grain should be is inside the inner pipe of the combustion chamber. It's easy to assemble the engine and after the test take apart. So if you look at the fluid control diagram, we have a lot of different, of course, valves, regulators, and timers, because the process of the combustion takes about 15 seconds only. So we use a data acquisition system, National Instrument Data Acquisition System, to collect all data, starting from run of the engine. The system run of the engine, collect all data, and stop combustion. Well, in order to initiate the combustion, we use injection of propane. That's why you see a propane tank here, just for 1 second. And the main tank with oxidizer, of course, it's oxygen tank, and we supply oxygen through the system of the valves and valves into the combustion chamber. The picture of test facility is here. Well, what parameters we measure? We measure pressure in the combustion chamber. You can see 2 pressure transducers here. Pressure at the entrance to the oxygen flow meter. Flow rate of oxygen. Temperature of the exhaust plume. because we would like to know temperature in the combustion chamber, and how we do it. We measure temperature of the exhaust plume and then recalculate the temperature and get temperature in the combustion chamber using our own model, mathematical model. And engine thrust, load cell is here. We measure engine thrust. All data are collected and processed by data acquisition system. Some challenges which research team or teams faced with. Void formation. So during the fabrication, during the solidification of the grain, so you can see here test fixture for the fabrication of cylindrical solid grain and two molds, inner mold like rod and outer mold like cylinder. Because of relatively low temperature, initial temperature of the molds and high temperature, it's about 60-70 degrees in Celsius, of paraffin or beeswax or these fuels with aluminum powder. Of course, because of temperature difference during the solidification of the grain, we observe the formation of the voids. Voids is not good idea. I mean, formation of the voids is pretty bad because in this case the combustion area of the grain during the combustion goes up, or the fuel goes up, but we have to have the stable increase of the real burnout surface from here to here to here. That's why the goal was minimize the void formation. Two solutions were proposed. Preheat both molds up to the temperature of the liquid paraffin or beeswax, or maybe install the heater in the internal mold. It's our mold, sorry. It's our future, idea, future design. Another one is we faced with the failure of the graphite nozzle. The engine has graphite nozzle. It's here, and we found out that at high values of the initial diameter of the port grain, which is, as you remember, 2 inches, sometimes we face with the failure of the nozzle, of the nozzle because of impact of the high temperature flow. It's diagram here of the combustion products, which let's say push the graphite insert, and graphite, look at the picture, several times graphite insert was broken in this cross section approximately. We performed calculations. Unfortunately, we were not able to change the design of this nozzle, of the nozzle insert, because it could cause the change of the design of the flange. That's why we decided to limit the supply pressures, but it was specifically for 2.0 diameter of the inner grain port, and do not perform the tests at the pressures, oxygen supply pressures, which are higher than 120 psi. As for the rest diameters, everything was okay. Collection of unburned fuel, because after each test, of course, we have the unburned amount of the fuel. Look, it's cross-section, not cross-section, but it's grain before and grain after the combustion. But the best way is collect the fuel, unburned fuel, right after the combustion. It should be done very fast, as the steps of the collection shown here. So team should immediately take apart the rear flange of the engine and remove all unburned fuel, because the only way to find mass flow rate of fuel is weight of the fuel grain before the test and weight the rest of the fuel which was not burned after the test, and of course calculate the difference and divide this difference by the time. Then we have special formula. I'll show this formula for the recalculation of the weight of the burnout fuel into the regression rate, which we measure in millimeters per second. Well, one more challenge. Because the project, each part of the project takes just 1 semester. After 1 semester, we have change of the team members. That's why project management, it's a very important problem. So we have new student team which start to work on the project each semester. The solution was proposed, and based on our experience, involve more volunteers and sophomore, from even sophomore and junior and even freshman students, because generally this project was assigned for senior students. So we try to involve volunteers in the project, and in this case it's extremely beneficial for the knowledge transfer period. So our students, senior students, work with volunteers, and then volunteers already have the experience how to run the engine, how to take apart, how to process the data, how to collect the data, how to perform the analysis of the data. It's just main challenges which teams faced with. About results of current study. As I already mentioned, current study was study of combustion of paraffin enriched by aluminum powder. I already mentioned what kind of aluminum powder we use. So here you can see formula, conventional formula of paraffin with 10% of aluminum powder, and I promised you to show the formula for the calculation of regression rate, R lowercase dot, which depends on the mass of the, or mass, look, mass flow rate times time of the combustion, mass of burnout fuel. So we create the model for the calculation of regression rates, and regression rate should be measured in millimeters per second. So it's linear velocity of the, when surface of the burnout surface goes down, burnout perpendicular to direction of the radius. Well, a little bit about our results. On this slide, you can find the plots which show change of regression rates. It's vertical axis, it's regression rates here in millimeters per second, versus different parameters, versus oxygen mass flow rate, oxygen mass flux. The formulas are, general formulas are shown here, versus pressure in the combustion chamber, versus mass flow rate of propellant, and versus equivalence ratio. So 5 different options to represent regression rates. We can see a reasonable trend. First of all, increase of regression rates with the reduction of initial inner port diameters. It's exactly what we have here. Look, the highest regression rates were demonstrated for small initial diameters of the ports, then it goes down, goes down, goes down. It's reasonable because when we reduce the inner diameter of the port, we increase the velocity of the flow of the combustion products through the grain port. In this case, the heat transfer convection goes up, temperature of the surface of the combustion of the grain go up. So that's why, of course, we have more intensive combustion. Another trend, and it's exactly the same everywhere, another trend is regression rate goes up with the increase of oxygen mass flow rate. Look at the plot, this plot, with the increase of mass flux of oxygen, with the increase of in-chamber pressure, with the increase of propellant mass flow rate, and with the increase of equivalence ratio alpha. It's reasonable as well because when we increase, for example, mass flow rate of oxygen, of course, we increase for the same variation of for the same inner diameter of the port, of course, we increase the velocity of the combustion products, and convective heat flow rate goes up, which increases the efficiency of the combustion. Here you can find combination. Of course, it's big scatter of the results of the data points, but it's understandable because these plots show the combination of the results of regression rates combined for all initial inner diameters of the solid grains. And again, the arguments are mass flow rate of oxidizer, mass flux of oxidizer, mass flow rate of the propellant, pressure in the combustion chamber, and equivalence ratio. By the way, why we proposed equivalent ratio? Because equivalence ratio combines both mass flow rate of fuel, mass flow rate of oxidizer, stoichiometric ratio of mass flow rate of oxidizer and fuel. So it's a combination of almost all important parameters. That's why we found out that equivalence ratio is pretty good argument which combines all arguments which are listed here. Well, on this slide you can find the results of the study of combustion of pure paraffin. It's previous, and on next slides you find comparison of the regression rates in the case of the combustion of pure paraffin and paraffin with aluminum powder. It's exactly what we have here. It's samples of the plots. First plot, it's a change of regression rates in the case of the combustion of paraffin and pure paraffin and pure paraffin with aluminum powder. It's orange points, data points, versus oxygen mass flow rate. So I'll pay more attention to this plot as example. Then we have the same versus oxygen mass flow rate, but for different inner diameter of the port, 0.5 here and 1 inch here. Then versus oxygen mass flow rate for a grain port diameter of 1.5. This slide from grain port, it's maximum one, 2 inches. And then change of argument, so it's regression rate versus in chamber pressures. So if you look at these plots, we can state that efficiency of the combustion, I mean regression rates, mostly we are speaking about regression rates, for the combustion of paraffin plus aluminum powder higher than regression rates in the case of the combustion of paraffin. It depends on the values, speaking about this plot for example, it depends on the values of oxygen mass flow rate. Somewhere we can see increase of the look, for example, this data point, increase of regression rates in the case of addition of aluminum powder, sometimes reduction, as you see here. Probably it depends on the, you remember I told that it's pretty contradictory data. It depends on the size of particles of aluminum powder. And as you remember, we used aluminum powder particles with a diameter which is between minimum and maximum size. So it's possible even find, by the way, if you look at this plot, for example, for the inner port diameter of 2 inches, the regression rates for the combustion of paraffin with aluminum powder much higher than regression rates of the combustion of pure paraffin. Probably it's because of initially high area, burnout area, because if we compare initial and current burnout area for the grain with diameter of 0.5 and solid fuel grain with initial diameter of 2 inches, of course, this diameter of this solid grain, initial diameter of the surface of the solid grain much higher. Probably we have, let's say, enough area in order to burn out the particles of the aluminum compared to this small area. So it's much more possibility to burn out completely the aluminum particles. Okay. So, but nevertheless, it requires more research. Well, the same comparison based on different parameters. So you can find here the plots which show the comparison of the regression rates of the combustion of pure paraffin and paraffin with aluminum powder for different port diameters versus in chamber pressure, again in chamber pressure, so variable port diameters, and versus equivalence ratios as well, the last 5 plots. So it's change of regression rates in the case of the combustion of pure paraffin and pure paraffin with aluminum powder for the grain ports of 0.5, 1 inch, 1.5 and 2 inches. versus change of regression rates versus equivalence ratios. Well, here it's just samples of change of samples of the formulas, because final goal, of course, is represent our results of our study through the formulas for the calculation of regression rates versus parameters which I mentioned. It's just part of our formulas. You can find here 10 different, 1, 2, 3, 4, 5, 6, 7, about 10 different formulas as change of regression rates versus mass flow rate of oxygen, and change of the regression rates, formulas are here, versus equivalence ratios. Well, project outcomes. First of all, this semester we obtained new regression rate formulas which describe regression rates of the combustion of paraffin with 10% of aluminum powder. Also, of course, project provides senior students and other students with excellent opportunity to work in team, perform the research, real research. Of course, they gain a lot of hands-on skills, managerial skills, communication skills, and had the chance to apply their knowledge to the resolving of engineering and scientific real-world problems. Also, of course, during this project, students applied knowledge from the courses which they already took: thermodynamics, fluid mechanics, combustion, propulsion systems, so on and so forth. And finally, I can run the video of the run of the engine. Thank you so much. I'll be more than happy to answer your questions. Thank you.